All right, so this video is a continuation of our study about volumes of solids, and we are going to continue using cross-sections just like we did before, but this time we're not taking a shaded region and rotating it. There will be no rotations today. Today, the shaded region is going to be the base shape for the solid that you're going to create. And the cross sections aren't necessarily going to just be circles or just be washers. The cross sections could be triangles, equilateral triangles, isosceles triangles, right triangles. We could have squares, we could have rectangles, we could have hexagons, we could have pentagons. We're going to have all sorts of different cross sections that we can use. So I went ahead and I made the base of my solid bounded by the square root of x and y equals 0, so the x-axis, and a line x equals 4. So this is the base of our shaded region. And the cross sections that I'm going to use are actually going to be squares with a semicircle on top of them. All right, so that's what we're going to do. So we have to picture it that we're taking a slice here, slice, 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 infinitely many slices of that cross section. And of course I can't do that. That'd be really hard to do infinitely many. So I'm just going to do slices at specific points on the graph. So my first cross section is going to be at 0.25 for the x-coordinate. So that means at 0.25 that the base of my cross section is going to be a length of 0.5. All right, so if I look at this, I've got a little square with a semicircle on top, and the square is 0.5 by 0.5, and the semicircle has a diameter of 0.5. Okay, so if you look at this, we can see there's the 3D nature of my figure now. So the base is still this shape, and this little square with a semicircle on top makes it about that tall. I don't have some filled in here, but if you can imagine that this one would be like itty bitty, and then it would kind of curve up and have this shape. So it's straight on this side and then kind of curves, it's rounded on the top. So if I'm looking at the next one that I'm going to do, my next one I'm going to put at an x value of 0.5. And if I measure this right here, if I plug in 0.5 to the equation, that means that my square is going to have a base length of 0.707. So if I look at this square with a semicircle on top, the square is 0.707 this way, 0.707 that way, and then the semicircle has a diameter of 0.707. Okay, I went ahead and did a bunch of them all at once. So if we just kind of look at this, then you can kind of see, so my base has that shape, right? And then as the base gets wider and wider, these cross sections get bigger and bigger. And if you can look at this in 3D, then we have this solid object right here that kind of has this, it goes straight up on the sides because that's the square part, and then it's rounded at the top. So as the radius, well, not the radius really, but you can kind of think of it as the radius or that width there as that gets bigger. So for our last one, I'm plugging in 4 as the x value, so that means that the base of my square has a length of 2, the height of my square has a length of 2, the diameter of my circle, semicircle has a length of 2 as well. So in the past, if you remember like middle school math, if you wanted to find the volume, let's say, of maybe a box of cereal, you could say the area of that base is a rectangle. So you'd find the area of the base, and then you'd multiply it by the height of the box. And that would be length times width times height, and that would give you the volume of cereal that you had. Or maybe there's those tubes kind of like oatmeal. They come in usually circular cases like cylinders, and so if you wanted to find the volume of oatmeal, you could say the area of the base, which happens to be a circle, multiplied by the height, and so that would give you the overall volume. So we're kind of doing the same thing here, where instead of saying we have something that goes straight up and down, we have something that kind of gets bigger depending on what the base shape is. But what we can do to find the volume of this is we can say, I'm going to look at the area of the cross section multiplied by the width of the cross section, and that's what that dx is going to be every time. So when you write your integral from 0 to 4, we're going to have the area of the cross section times the width, and actually we'd be adding these all together, right? Infinitely many of these that we're all adding together, and that's how an integral works. So again, when we write our integral down, we just have to have a formula that describes the area right here, and then we're going to integrate that formula and then have the dx, which represents the width, and that will tell us the volume of this solid. That's what we're going to be working on. All right. So the notes that I gave you in class look like this, and that means that for us to be able to do these different solids, we have to know what our different formulas are for our cross sections. So if you can picture this, we have the area of a square we know is side times side. So if you look at this, the area, the side of your square is based off of how wide that piece is for your base area. And so we're going to use S for slice, like if you take a slice of that, that's what that is. And so the square is going to be the side of the slice multiplied by slice. So we're going to say that the area of a square for the formula is going to be S squared, or side squared, or you can think of what the slice is squared. The area of a semicircle, if you can see the semicircle and kind of compare it to what would have been down here, the length of the semicircle is this length right here. And so we're still using that idea that we did before of saying top minus bottom or right minus left. And I did not mention that when I was talking about the square, but this S would have been top minus bottom, where the top is the root x and the bottom is 0, for us to be able to find that. So here we're going to say that the diameter of the semicircle is going to be whatever that S value is, that slice, that top minus bottom. So here, I know that the area of a circle is pi r squared. I'm going to put this work off to the side. I know pi r squared is the area of a circle. And I know that in this case we are given the diameter. The picture that we have, oops, the picture that we have here has the diameter of the semicircle, not the radius that's given to us. And so I know that if the diameter is what we're calling S, from S squared, then I know that my radius is going to be half of S. So that means that the area of my semicircle is going to be pi r squared, or pi times 1/2 of S squared. And a semicircle is taking that circle and cutting it in half. So that means I really should have had a 1/2 in here since it's half of a circle. And I really should have a 1/2 in front of here since that's half of a circle. So if I simplify this all out and kind of multiply this stuff, that gives me 1/2 pi. And then 1/2 times 1/2 is 1/4 S squared. So the area that we're going to use for a semicircle, if we're talking about these cross sections that we're slicing into, we're going to say it is 1/8 pi S squared. All right, and it's actually good. Let's go ahead and write off to the side. S is top minus bottom, or right minus left. Okay, so that's how you figure out how big your slice is. All right, area of a triangle, we're going to go back to this and kind of picture it. If we had triangles coming up here instead of squares, we know that the area of a triangle is 1/2 base times height, but if you can see that the base of the triangle would be that S value. So we're going to say that the area of a triangle is 1/2 S times H. So 1/2 base times height, but the base is going to be whatever that S value is, that top minus bottom. The area of an equilateral triangle is going to be √3/4 times S squared. And when we do the area of a rectangle, we have two different formulas we look at. We usually do base times height. So if you can picture this being a rectangle instead of a square, base times height. So the base would be that S value and the height would be whatever H value they happen to give you. So area of a rectangle is going to be S multiplied by H, or they also might say length times width. And so in this case, we would call this the width of the rectangle, and the length of the rectangle would go up and down. So whichever way they give it to you, that bottom part that goes against the shaded region is what the S value represents. So L times S. Okay, so here are some important things that I want you to highlight and remember. The solid is not being revolved around an axis. It is perpendicular along an axis. So this is perpendicular to the x-axis, it's sticking straight up from right there, okay? We are not taking something and spinning it around. This part, you can tell these are important because they were probably in color on the original document that we got them from, but it's highlighted down here actually. If you are perpendicular to the x-axis, then everything that you write for your integral needs to be in terms of x. If you're perpendicular to the y-axis, then everything that you write in your integral needs to be in terms of y, which kind of makes sense because this is still what we're talking about as far as it being top minus bottom and right minus left. So we're being consistent with what we've learned before. So we're going to make sure that we keep all of these things in mind when we start to write our integral. Okay, so what I want to do, you don't have to write down this part since I've just been kind of using this as a visual to show you, but I want to show you guys how we would find the volume for this. So when I look at the integral, I know that I'm going to be integrating this from 0 to 4, and I can see that my solid is perpendicular to the x-axis, right? So I'm doing top minus bottom. So if I look at this, I have two different shapes. I have the square shape, right? And then I have the semicircle shape. So that means that when I do this problem, I'm going to be doing s squared plus 1/8 pi s squared. And it will be in terms of x, so it would be dx. And I know that my s is figured out when I do the function, the top minus the bottom. So the top is the square root of x, the bottom is the x-axis, which is 0. And so for me to find the volume of this particular shape of the way that I did it, and you guys are going to do this tomorrow, you guys are just going to have different cross sections than I have right now. And so I'm going to say that that would be square root of x squared plus 1/8 pi square root of x squared dx. And if you plug that into your calculator to evaluate it, you're going to find that the volume of the object that I showed you, that solid that I showed you, is 11.142 units cubed. So really, these problems aren't much more difficult than what we did as far as our rotations to find the volume. It's just quite a bit different for you guys to be able to picture exactly what you're doing.